Good morning, everybody. So my talk is a little bit different than the ones that we have seen before because I'm concentrating on how Keuka is innovating in this whole process of innovation in Europe. My name is Bischoff. I'm the head of technology development of Keuka Laboratories, and I'm also the vice president of the Robotics Association, e-Robotics ASBL, and you will see how this is all connected in my presentation. So Keuka is known as the world's largest manufacturer of industrial robots for the automotive industry. And you see here our three companies, Keuka Roboter, Keuka Laboratories, and Keuka Systems. And in the low row, you can see also how our business is distributed to the different sectors. And just from the figures that you see below, automotive, 50% on the Keuka Robotics business, and even 90% on the Keuka Systems business, you see that we have a high dependency on the automotive industry. And what we try is to diversify and also to bring our robot technology in different branches of the industry. And therefore we founded Keuka Laboratories. Keuka Laboratories is a company that is now developing robotics technology also for the medical sector. But if you want to put it in short words, it's our service robotics company. And I have been asked to point out in my presentation about the innovation that we are doing with industrial robotics. Industrial robotics, of course, there has to be, we have very close relationship to our customers. So customers are at the heart of our business, and this is already driving one part of the innovation. But if we only listen to our customers, you know probably the famous sentence from Henry Ford, if I had asked my customers what they wanted, they would have said a faster horse. And the same applies to robotics. So no one would have ever said, would have come up with the innovations that we have come up in the past years without a technology push where we really rely on a close collaboration with academia. And this is how we see the innovation potential in the robotics business today. So we all know the industrial robotics business. We have PC-based robots controllers. We know offline programming, and we like to refer to this as the first robotic revolution that happened with the advent of these industrial robots. Now we are at the borderline to the second robotic revolution, and this will happen because we have very good knowledge about the mechatronics of our systems, about how we integrate safety with these robots and how we do more simpler programming and operation of these robots. And here you see depicted the Keuka lightweight robot, which is compliant, safe, and this will allow us from now onwards to go on with the second robotic revolution. And on top of that, we try to make these robots mobile and to yield mobile manipulators, which would go to the third robotic revolution, where we combine mobility and manipulation, where we have more intelligence on board these robot systems, and where we go from a programming to more intuitive operation. So I'd like to focus now on these three steps of the robotic revolution. So first looking again at industrial robotics with the PC-based controllers. If you just look back, this was one of the key innovations that we did already in 1996 to switch from proprietary controllers to an open PC-based controllers. If you just see at the number of robots that had been produced until 1996, this were 12,000 in total over the years. And since we introduced the PC-based controller, we had a major rise in our business because the PC-based controller was open and many customers were following, and now all major robot manufacturers are using PC-based robot controllers. Second example, in 2010, we introduced a new robot series, the Quantex series. This is one of the things that we try to bring in the potential from mechatronic technology development. We always have to reduce the volume of our robots, to reduce the weight, so that we can reduce also energy consumption and to be faster in our production. This is one thing. And then another thing is how we are going to save on spare parts and how we make the life easier for our system integrators to maintain and repair, for instance, robots. We simply replace hardware by software. So ICT technology is very important for us here. Energy efficiency for a sustainable production is important. For instance, by forecasting the consumption of robots in simulation is one important aspect. But also important are the manufacturing processes. So we are still developing new joining processes. So if you think that welding is a solved problem, it is not. So even in welding, you are able to innovate. And for instance, what you see depicted here is a robo-spin technology. When you just look at simple spot welding robots that are used nowadays, they simply go from one spot to the next, to the next, to the next. But there's still an innovation potential. If you just rotate the welding gun while you are pressing the material, you can already save some time while you are moving, and you can also save your welding gun, and the welding gun tips are much better used. So there's always new things to detect and to develop. One part is also energy efficiency. This is a nice, interesting figure. So from left to right, you see some of the robots in a typical automotive production. So only 19% of the time our robots are actually in motion. 81% of the time they are not in motion. So we have to look into this, why they are not in motion. So some 10% of the time they are stopped with active drives, which means there's no brakes engaged. Then they are stopped 26% of the time with brakes engaged. Stopped 10 minutes, from 10 minutes to 3 hours, and they are stopped over the weekend for 28% of the time. But what is happening, our customers are not switching off their plant. They keep it running all the time, so this means there's a huge potential here to save on energy. And we did something in that area, on each of these areas, only a little bit, but as I explained just now, the Quantec series, because it's more lightweight, it's already saving energy while it is in motion. Then we have a technology called blended braking, which engages the brakes much earlier than before, which saves energy. Even if you think this is a little bit ridiculous to have a temperature-controlled fan, it is also helping us to save energy here. And then there are simple standby modes that you all know from a PC technology. You can send your PC into sleep mode and save more energy. And now this is also possible with robot controllers. This might sound simple, but the difficult thing is to wake up the robot controller after it has gone into sleep mode, and that all the peripheral equipment is coming up again as well. So through these technologies, we are able to save energy on the shop floor. So very important aspect in industrial robotics. But as I mentioned before, the major innovation step came from the PC-based controller, and all the other innovations are then adding incrementally on that level. So the next disruptive change in robotics is through the compliant and safe robotics technology. The Keuka lightweight robot here, you can ask why we have developed that robot, and this is because we need sensitive robotics on the shop floor. To enable totally new assembly concepts, to enable the collaboration between humans and robots, and then most importantly to relieve the worker at unergonomic and bad workplaces. And finally, to keep production in high-wage countries. So that's why we need this robot system. And what did we do? We integrated torque sensors, and we integrated safety technology on drive level. And this integrated safety technology is complying to the norms. This means ISO 10-18, performance level D, and structural safety category 3. There's a lightweight construction in this robot, and we have a powerful operating system to make it easy for the customers to program and to operate it. So the robot is called IVA, an Intelligent Industrial Work Assistant. And I give you a few examples on what can be done with the robot system. First of all, I highlighted now in orange, that's the kind of functionality that is now enabled by the robot. And to give you an idea about the functionality, I have 4 videos. That should pop up now on the next slide. Without the sound, please. Okay, so here you see the interesting features of that robot system. So first of all, to the left top corner, you see the gravity compensation that is enabled by the robot. So while the robot is carrying 7 kilograms, you can easily move the weight around. So you can, for instance, teach the robot by demonstrating where to move with the payload. It's just 100 grams that you need to move the robot, but still it has a payload of up to 7 kilograms. Then to the right top corner, you see the kinematic redundancy. It has 7 degrees of freedom instead of 6. With these 7 degrees of freedom, you can reach around corners, you can reach difficult situations on your workplace. And in the lower row, you see a special feature that looks like a spring. It's basically like a human arm that you can push away, that has also certain damping characteristics and salt and stiffness characteristics that you can program on an axis or joint level, but that you can also program on a Cartesian level. And what you can do with these nice technical features, we have to demonstrate with our customers so that they see what they can use. Here is a picture of a manual assembly of a differential gear. So that's a very difficult and unergonomic situation because the gear is heavy and you have to use your both arms to fiddle this gear into the gear house. Daimler did this with a very complex gripper technology. So to the left you see depicted this gripper. It is very complex. It has, in order to do that compliant motion, it needs mechanical compliance. This gripper has low flexibility. It's only working for this type of gear. It has complex engineering. Just look at the picture, and is associated to this high cost. Now the simple solution with the lightweight robot is you can have much simpler grippers because all the compliance that you need is inbuilt into the robot arm. So you compensate through software. This gives you high flexibility, gives you much more simpler engineering, and then accordingly low cost for the grippers. I have a video here on how this is being used at Daimler today. This is a rear axle transmission assembly, which was done manually and then with a complex gripper. And now we have the lightweight robot, which is able to lift with the help of a balancing system this gearbox, or the gear, which is then inserted into the gearbox in a kind of dual arm setup operation. So the second arm is coming from below, and both together they are pushing this into the housing. And then you see an operation that also a human would do. There's a kind of shaky motion at the flange that you see. So the robot is moving like this, and this is helping to fiddle in the gear into the housing. So the same operation that a human would do can now be done with these robot systems with much simpler grippers than it was able before. So now to focus on the second, so this was the sensitivity aspect, which is very important for robotics of the future, or for the automation of the future. The second important aspect is now highlighted in orange, and that's the collaboration between a human and a robot. And therefore you need to have safe robot systems which comply to the safety norms. And why this is important? Because the system integrator in the end has to do a risk analysis for the cell that he has to set up. And he has to make the certification of that cell so that the end user is able to use the system. And what is important in this respect is that we are now able with this robot to not only program a velocity for the robot, but to guarantee that this velocity is not surpassed, even if an error in the hardware is occurring or if an error in the software would occur. So safe velocity monitoring, safe workspace, and safeguarded zones. This is also needed to set up human-robot workplaces. Safe collision detection, safe force monitoring, safe tool detection is also needed. You need to know what kind of tools are put to the robot, and safe switching of states. And all this in performance level D, category 3. This is something for the experts. If you don't have this performance level, you would have a hard time as a system integrator to justify why you can remove all fences around the robot system. Also a video to demonstrate what we actually mean with this. So here you see someone again guiding the lightweight robot, and you also see the workspaces that have been set up. So the robot would not be able to go outside these virtually set up workspaces, the fences. There's a velocity monitoring integrated in safe technology. This means if the robot is moving too fast, it will simply stop. And then this safe collision detection. First, the crushing. So crushing means that the robot wants to insert something, but then detects that there's a human hand inside, and the robot is able to detect that and will automatically retract. Or the safe collision detection in a free collision. So when the robot and with the tool are going to the human, the robot will notice this and then can continue with the process. Okay, this brings me to this third revolution. We have to put these arms onto mobile platforms to be able to simplify the shop floor logistics and manipulation. There's one example now. Now we are going to the future. So this has not yet been realized or just in research projects. We are engaged in many research projects in robotics. One of them is TAPAS. And here we are collaborating with Grundfos as an end user. What you see here depicted are some examples of a Grundfos shop floor. To the left, you see a machine tool. This machine tool has to be fed by the robot system. To the top, you see a quality station, also to be served by a mobile robot system. If you want to move around on the shop floor, you need things like lifelong mapping and local navigation. And there's also manual workstations that just have to be served by such a robot system for simple assembly tasks. And here I have just a video that we did recently at Grundfos for our final evaluation. You see that we are far from having done this at a level that this can be used at a production, but it just gives you an idea that you have a robot that is now able to fully autonomously navigate on the shop floor, so no additional markers are needed. And then you can use the robot to feed workstations. You can use the robot to pick up objects from location A to bring it to location B. Here you just saw the robot switching off a conveyor belt by using just its own motion capability to stop the conveyor belt and then be able to pick up the object. This robot is equipped with an external stereo vision system. It has autonomous path planning for the robot arm. And what you also see, the video is much accelerated. Actually, it's accelerated by the factor 8. So this also gives you an idea that this technology is not yet ready for the shop floor because we are too slow with all the nice scientific things that we are doing. So there's still an order of magnitude or maybe even 2 orders of magnitude improvement needed in this case. Navigation is quite reliably already. So these are some of the challenges that we still see from a scientific and also from an industrial point of view, which would make nice projects. Each of the lines that you can see here should be targeted by researchers. And what makes it even more important or even more difficult, if we look into the industrial requirements that go all along with these scientific challenges. So you have to reduce the setup time of such a system. In the Grundfos scenario I just demonstrated, we had 2.5 days to set up the whole system. This is much too long. So this has to be set up in 2.5 hours, not in 2.5 days. Cycle time, I mentioned already, video was much accelerated. The dependability, it has to work 100%. Technology readiness is not there yet. And of course, the cost is much too high to really be of help to manufacturing companies. So if you look at these core technologies for mobile manipulation, you all know these terms: end effector, safety control, locomotion, navigation, sensor, sensing and perception, human-machine interface, planning, learning, system architecture, system engineering tools. All these are core technologies that we need for mobile manipulation. A very important question is on how to combine all these into one system and what technologies to use. So there's one thing, so how to integrate them into a complete system, how to achieve reliability, and I'm standing here saying, so this is long before it will be applied into the industry, so further research and development is definitely necessary, and the big question is, what is Keuka doing to speed up this process? And I have 2 answers to that. So one answer is we are trying to drive innovations through collaboration with academia. We are very much engaged into the EU Robotics ARSBL, that's our European Robotics Association. We do now have more than 180 members from industry and research. About 1/3 is coming from industry, 2/3 are coming from research. And this EU Robotics ARSBL is also the private side of the public-private partnership with the European side. It was introduced yesterday already. It's called SPARK, the Partnership for Robotics in Europe. And through this partnership and through our colleagues from industry and research, we try to set up a roadmap, and through that roadmap then, of course, to influence the research that is being done in the field of mobile manipulation. So next slide is not coming. Maybe you can do that manually. So there's a collaborative road mapping process in EU Robotics AISBL. Of course, it's important to be a member, to be able to vote on priorities, but also non-members. If you think you are an expert and can contribute to these technologies, you are invited to collaborate with us in the so-called topic groups. And these topic groups are then giving their input to our strategic research agenda. That's a high-level political document. And then, most importantly, to the multi-annual roadmap, which will be updated biannually and which is then used to discuss with the Commission what could be priorities for the next calls. And this collaboration is, I think, really driving us to innovation in the long run in robotics as a whole. And the second answer to the question, what is Keuka to speed up the process? We are developing robots that can be used in research and that can be used or that can be seen as standard tools for education, application development and research. Here's the Keuka U-Bot as one example. It's a mobile platform with an industrial but little robot arm. It has real-time Ethernet communication. It's the same communication we use in our big robots. It's freely programmable. There's open source library available. And we think that it's important to have such standard platforms to enable researchers to focus on their research, to benchmark their research with others, to participate in competitions, and to better market their results. Because if this becomes comparable through the use of standard platforms, it's much easier for companies to compare. So this brings me already to the last slide of my presentation, summary and conclusion. I think that research is very important. Although I'm standing here as an industry person, I think we should not neglect the research part. And many of the technologies identified in the European Strategic Research Agenda are needed to realize mobile manipulation for the factory of the future. Then the second thing is that integration is important, but we have to avoid to reinvent the wheel by always developing new robot systems. You should also try to use standard platforms which help to reinvent the wheel. I think also that competitions are important, and there will be a session in the afternoon on competitions related to EUROC, the European Robotics Challenges. But there's more competitions around. Also Keuka has just recently spent 20,000 euro for the winner of the Keuka Innovation Award, which was on the area of mobile manipulation. And these competitions are important to create a better awareness and to allow for benchmarking. And last but not least, collaboration is important. To collaborate not only within the industry players, but also between academia and industry. And here we have two major initiatives, our Robotics Association, please apply for membership, and Spark, the program for robotics in Europe. Thank you for your attention.